Hey, good morning, good afternoon, good evening, everyone. Thank you for attending our July webinar hosted by the San Diego Fort Collins, sorry, Fort Collins, San Diego IEEE Big Chapter Talk. We are really thankful today to have Sam Naffziger from AMD present talk on his views and all the exciting advances that's been happening in the chiplet space at AMD. Okay, so just a little bit of logistics. Basically, if you have some questions, please ask your questions at the bottom in the Q&A window, and we will stop to take Q&A somewhere in the middle, and then also at the end of the presentation. Okay, so anyways, let's get going with the main event. Let me just briefly introduce Sam. Sam is definitely no stranger to the community of processors, high-performance compute processors. He's an AMD Senior Vice President and Corporate Fellow at AMD. He's also a Product Technology Architect, and Sam has been driving basically the direction for processors for as long as I can remember, when my a small humble cubicle was beside his big office for many years. Anyways, Sam's role largely as an architect is to basically do best practices, power performance area methodologies for product competitiveness, cost, so forth. He's been the lead innovator behind many of AMD's low power features and chiplet architecture. Been in the industry for over 3 decades with background in processors and design at HP, Intel, and then AMD. Sam has a bachelor's from Caltech and a master's from Stanford. He obviously is very well known in the industry in the space. Yeah, and also an IEEE fellow. Okay, so without any further ado, Sam, it's an absolute honor to have you speak at our chapter. Take time out of your busy schedule, and we look forward to hearing your talk. Thank you.
Great, thanks, Alvin. Yeah, fun to be here. I always love talking about technology to technologists across our industry. So, and I do, want this to be interactive, like Alvin mentioned. So I'll pause for questions at various points in the presentation, and love to get your questions or comments. So, yeah, the talk here is focused on chiplet-based future and the technology implications for our products. And obviously, I'm presuming the future is chiplet-based, and I will walk you through why I believe that's the case. I'll start with an overview of what's driving compute in our industry. There we go. And why we will have more demand for compute than legacy approaches can provide, and then get into some of the packaging innovations that are going to be fundamental to meeting that worldwide demand for compute, and the various technology improvements and innovations that are going to be required to where we need to go. So, it's a super exciting time to be in our field. The demand has never been higher, and the outlook for increased compute demand is only increasing. Got a lot of people out there using connected devices, generating data at astonishing rates, 163 exabytes in 2025. So, that data is only as useful as the processing that can be applied to it. So we got this wave of big data coming, and to make use of it for the worldwide community, to turn it into valuable knowledge that improves our lives, we got to process it, and that drives computational demand. So this is the reality that we're facing. It's inexorable. The connected devices, the user base is driving this explosion. And maybe one of the easiest ways to see how that is playing out is in the field of machine learning and the spectacular growth in the compute requirements for these networks. Of course, as everybody on the call is aware, right, the capabilities of these machine learning systems has been improving dramatically, reaching human level ability to recognize and recognize language, recognize images, etc. But in order to do that and make these machines so valuable to humans, they require a huge amount of compute training. The graph on the right there shows the increase in the number of parameters for these neural networks and log scale, right? So it's growing truly dramatically, doubling every 2.3 months. And there are various other graphs that some of you have probably seen around the computational requirements to train these huge networks. And Moore's law was a doubling of every 18 to 24 months. The compute requirement measured in petaflop per second days is doubling every 3.4 months. So obviously we are way outstripping the Moore's law pace of improvement, even as Moore's law is slowing down. So that just sets the context for the level of computation that this big data wave is requiring. And plotted out, the SRC has done some good forward-looking analysis in their decadal plan that came out last year, and I think that sets up the problem pretty well also. So the demand for compute is definitely outpacing Moore's law, and fundamental conventional approaches to compute are not going to suffice to meet that demand. And one way to look at this, there's a lot of ways you can look at it economically. You can look at it in just silicon requirements, or in energy as here, right? But the compute energy required to meet trend in demand is growing much faster than the worldwide energy production capability. Obviously, we can't have compute devices consuming all of our world's energy, so we need to have more efficient approaches. So that is one of the drivers for new architectures, new capabilities, and we can also see that in this very interesting chart, also from the SRC, that shows an empirical plot here of the instructions per second. So this is CPU focused, and it's showing basically the IPC, right? The compute capability of these processors, and plotted against the number of bits switched to achieve that instruction throughput. And so it's it's kind of like an architectural efficiency. And the ideal case would be that if you switch double the number of bits, you get double the performance, right? But it's not even close to that correlation. That one-to-one is shown here on the green curve. But the empirical actuals are that it takes a lot more bits switching to get a doubling of performance than 2x. And that any of us who have been involved in computer architecture and design know that's true. IPC is hard to come by, high frequency, requires a lot of engineering, faster gates, architectural work. And so we need to generate a lot more compute, a lot more efficient compute, but we cannot afford to stay on this blue trend line. We have to be more efficient in the way we generate those instructions per second and get more towards the green line. So that means we have to improve our architectural efficiency. And that's made even more challenging with the trends that we see in our technology improvements. And I know many of you are well versed in this, but a quick review, the node refreshes are slowing down. and at the same time, they are delivering smaller increments of performance. And while they're delivering less performance slower, they are costing incrementally a lot more than they used to, and that's what this second chart here shows. So that means the economics of advanced technologies to meet the compute demand are becoming much more difficult. Now, we've been addressing these slowdowns through a variety of methods. We've been throwing additional silicon at the problem, and this chart here looks at server CPU and graphics processor die sizes over time. And they show a growth in absolute die size, not transistor count, but actual absolute die size, which means in order to stay on that compute improvement treadmill that the world demands, we are on an unsustainable path of adding silicon. And not only are there economic limits, these devices just get too expensive if we keep doing this, but there are practical manufacturing limits, reticle size, et cetera, that prevent us adding more transistors, more area. The other thing we've been doing, and this is just one way to look at the problem, is adding power. You look at the top supercomputers, they're generating a lot more performance, but it's also at higher power. So we're making our chips a lot bigger, and they're burning a lot more power in order to keep up with that compute demand. So unsustainable trends. We've got slowing transistor improvements and the things we've been doing recently to get our performance increases are not sustainable. All right, so what are we going to have to do? We need to change the compute energy trajectory. And we need to be more efficient in all dimensions, right? And that obviously we can't, as I showed there, right? Our efficiency in generating instructions per second is poor with legacy approaches. The demand is huge and increasing, so it's not sustainable, and we're going to have to move off of that curve to a more efficient one that generates more instructions with fewer bits switched. And the best way that we know of to do that is more special purpose accelerators. So that's why GPUs have become a lot more, have been proliferating in the compute space. And we also are seeing a move towards all manner of domain-specific accelerators. And over a decade, a lot can change. There's quantum on the horizon. There are other approaches that will get us down into fewer bits switched for a given level. We need new approaches. Hopefully, make that case clear. And the move to accelerators is one of those approaches. Now, special purpose domain specific accelerators are nothing new in a sense, right? We've been using these for graphics for many decades, and mobile phones and notebook processors, other processors are packed chock full of accelerators, right? And so I put here one of our recent Ryzen notebook processors, and we've got all kinds of accelerators in there for video, audio, security, display. And the CPU cores are here in the middle, and the GPU, which arguably is an accelerator, is down here. Then we have these other accelerators lined up around the periphery, and these are great for doing their specific tasks. They are much more efficient in compute per area and compute per joule for the tasks that they're designed for around video, audio, etc. So we know how to do accelerators, but their application needs to become more broad, more widespread. A good way to look at that is on this chart here, just a conceptual one, right? If you look at performance per watt and the breadth of the application space, everybody loves CPUs, and they are a dominant form of compute because they're so general purpose. So they're relatively easy to program and can address pretty much the entire application space. But their efficiency isn't great when compared to more special purpose devices, right? So, GPUs do really well at parallel compute tasks because of their wide parallel data paths and special purpose hardware. And we can do even better for a narrow range of applications with semi-custom SoCs and FPGAs. And so we as a company are taking that route along with others in bifurcating our architectures. So not only have we adopted GPUs for their particular application space, but now within the GPU family, we are splitting that architecture into a gaming optimized one that we call RDNA. So that has all the pixel processing and the texture capabilities and everything for 3D gaming. And then our compute GPU, and one could argue it's not really a GPU anymore because it really doesn't do graphics, it does compute, and doesn't have any pixel processing, for instance. And because we've jettisoned a lot of that graphics specific overhead, it can be a lot more efficient. So we get more computes per joule. With the CDNA architecture, we get more computes per millimeter squared. So it's just a response to the constraints that I just went through around die size increasing and running out of energy. We're going to see more of these trends towards special purpose. And there are a bunch of accelerators out there. Yeah, the industry's loaded with examples. Google's TPU, we even do a special purpose ASICs for crypto mining and audio, all these other approaches. Of course, deep learning is a huge frontier for developing these kinds of accelerators. And these accelerators done right provide much better area and power efficiency, orders of magnitude more general purpose. So where does this all lead? We got the increasing compute demand, significant barriers to traditional scaling. Hopefully I made a convincing case that we're going to need domain-specific accelerators to move off that very inefficient improvement line. And so that means we're going to need modular designs, because the key, the obvious conclusion here is, while special purpose accelerators are great for their particular task, they only address a small subset of the task worldwide that the community demands. And so we're going to need a lot of these special purpose accelerators for different markets. We don't have an infinite number of engineers, and no matter how much you pay us, we can only get so many designs done, so much work done in a given year. So we're going to have to be more efficient in the way we design these domain-specific accelerators and the way we hook them together to address particular market segments. So we need to be able to deliver more compute devices for more but smaller markets in order to keep the compute improvements going. And that means modular design. And that means we can't be designing these gigantic kitchen sink chips that attempt to do everything. They're just too expensive and they're insufficiently power efficient. We need to be able to design smaller, focused accelerator chiplets that can be hooked up in varying configurations and mixes to address different markets. That's what we mean by modular design. And I've thrown the ROCm here. This is AMD's version of the software stack that enables access to our accelerated compute infrastructure. Got to have the software that ties the accelerators together and makes them accessible. I'll pause here for questions if there's any. Yep.
Any questions? Oh yeah. Sam, a question came up. Question about FPGAs being less energy efficient. Can we assume it's in the same ballpark as with SoCs?
Well, that's good. I mean, FPGAs are intrinsically less efficient for the same task, but when there are very specific, and you can visualize it like a software and silicon kind of view, they can be a lot more efficient for very specific tasks if programmed properly. They're kind of the short-term um, way to address evolving protocols, and I mean, like in the 5G cellular space, for instance, right? Those a lot of that is highly evolving, and so then FPGAs can be better for those special purposes. But in general, no, an ASIC will always be more efficient for a given function.
Yeah. Do you have any, kind of like perhaps like a benchmark metric as to, the level of, what's on the table that a FPGA is less efficient by?
That's a good question. Yeah, no, I haven't benchmarked that.
Okay, no biggie. I was just
And it
curious.
depends.
It's such a broad
Yeah,
question, actually.
broad question. I mean, if you run a particular software routine on a general purpose CPU, it's going to be a lot less efficient than if you have an ASIC that's designed to accelerate that software routine, and the FPGA will be somewhere in between.
Yeah, sure. Yeah, yeah. Another question came up related to accelerators. So having the accelerator in modules creates like for a challenging management. Can you share one of the major challenges that you faced?
Well, the managing in what sense? I might get to some of that in the rest of the talk. I mean, they're software, interface challenges, which is a different view, and then there's the silicon interfaces between die, and then there's how to power management, how to test it properly. So there are a bunch of dimensions. I'll hit on some of those as we go through.
Okay, great. Yeah. And, also I'm kind of curious. I mean, we've got companies like Apple that are completely vertically integrated, and there's a lot of talk and chatter in conferences about the whole push towards hardware software co-design. I'm sure you're going to address some of that, right?
Well, I mean, it is an underlying theme in here. I'm not going to directly get into that.
Mhm.
It is, I mean, but that is why I have our software, in this modular system bubble, right? Because it is fundamental. And somehow we have to because we can't require ninja programmers to access these accelerators because there's a very limited supply of those. we need to make this these accelerators accessible with the more abstracted general purpose coding approaches that people are used to, and that's a huge challenge now. And NVIDIA and Apple have done a good job on that. There's industry consortia, and we're a big fan of open source, which enables real-time, evolution and adaptation of the software code base to the compute architectures as they're introduced. So we think we think open source is much more promising for making the accelerators accessible.
Makes plenty of sense. Yeah. Sam, would you like to continue? Looks like
well,
oh, you got a question?
So sorry, yeah. So I have two questions from our audience. They sent to us privately. So the first question is that do we see a comeback of a reconfigurable course to address domain-specific applications?
Yeah, reconfigurable computing. I mean, in a sense, that's like FPGA, right? And I think we are going to see a hybrid FPGA and compute accelerator architectures that do look like reconfigurable computing. what I'm talking about specifically here with modular design isn't so much that, but it's configurable computing, where we generate new devices like this Epic here with mixes of silicon compute accelerators, but they're all tightly connected on the module to behave as a monolithic SoC. So it's more, hard reconfigurable rather than soft reconfigurable.
Okay. Last one. What is the intuition behind the modular design being the solution? Modular design being the solution.
Well, yeah, I mean, I tried to lay the case out for that, right? In that, general purpose compute is intrinsically less efficient, yet we're not going to be able to meet the worldwide compute demand with these kinds of less efficient general purpose devices. We've got to go special purpose. And special purpose means you need a lot of these red bars, these red curves, right, to address the broad space that the green curve covers in applications. So if we need a dozen special purpose accelerators for what before took a single CPU, that means we need a dozen times the design teams for all the companies competing in this space, and that's just not feasible, right? So what we need to do is be able to mix and match these things in varying counts for the markets, and that the only way to do that efficiently, and my experience and our experience as a company, is with modular design. And I'll talk a little bit about some of that as I go further about how that's played out for us.
Owen?
Yep. Sounds good. Yep. No more questions I see. Yep. Sam?
Great.
We're good.
So I'll move into the chiplet concept itself. And back in the good old days, for much of my career, Moore's law was just a gravy train. We would get generational improvements that enabled us to double the amount of compute generationally, and boom, same size, same power. We had a great upgrade, and the doubling here was by adding features, capabilities to our general purpose processors, and of course, as I showed before, we were getting diminishing returns in the performance per second as we threw transistors at it, but it didn't really matter because Moore's law there was covering over a multitude of inefficiencies for us. Well, with the slowdown that we're seeing, we're instead of being the same size, we try to add the same amount of capability we did previously, we end up bigger. And as I showed on the plot, right, this has been happening in our processors and GPUs. They're bloating out generationally and sustainably. We can't continue that path. So it's inexorable here that if we're going to continue to improve our compute throughput capability, we're going to have to split these huge die up. So chiplets are inevitable in the computer architecture space. And what it looks like is, we take this die and now we got the same functionality in two smaller components. The challenge is that we have to add overhead to each of these die. So it's bigger than what a monolithic version would be in total silicon area, because the orange strips here, these die have to talk to each other. And then this extra stuff on the left and right is what we call chiplet overhead. These need to have their own PLLs. You can't share a single PLL. As in a monolithic, they need to have their own test infrastructure. They need to have their own power management controller, all this extra stuff, right? So that's the challenge with chiplets, but in net, they are still much better than the path that we're on with big monolithic. And I'll walk you through some data on that in a bit. The other significant benefit we get with this subdividing of these big monolithic die is first in yield and second in configurability. And when we get a wafer out of the fab, it has a certain number of defects, which is the reality we all live with. If we have only a few big die on that wafer, those defects will take out a large fraction of the total die. And now, granted, we can have redundancy and harvestability in these so that you can have down configured versions. They aren't completely dead, but at the end of the day, you end up with a lot fewer functional SoCs out of a wafer when the die are large. With very small die, you got the same number of defects on the wafer, but it takes out just a small die instead of a big one. You end up with a lot more good die. And now if you have the right test approaches, you can mix and match these things and generate a lot more functional SoCs, provided that they are architected to behave like a single SoC with chiplet interfaces, etc. The other thing we get is, if we're clever, we'll be able to determine which of these chiplets are the faster ones and which are slower, because we always have a speed distribution across a wafer. And we can build the fast ones with other fast ones, slow ones with slower ones. And now we have differentiation in our product line, which is the bread and butter of a lot of silicon companies like AMD. We want to sell premium products because some people really care about those last increments of performance. So many benefits with breaking up a large die into smaller ones. So I can run you through now a little bit of our history in pioneering this chiplet architecture. We really were the first mainstream company to go down this, computer company to go down this route. We started back in 2017 with the first generation EPYC, which is our code name for our servers. We needed to make a big splash. We were re-entering the server market after a hiatus, and we needed to exceed the competition's capability, which meant a lot of cores, a lot of memory interfaces, a lot of PCIe SerDes to make this an extremely capable differentiated server product. So we looked at the problem, and in order to do what we wanted to do, we would have had to have had a massive monolithic die. And that would be easy to design. We might not be able to fit it all in the reticle limit. We could have tried. And it, however, would have been extremely expensive. And if you know how these markets work, you can't sell your high-end, fully configured chip to most of the market. Most of the market wants down configured, cheaper ones. It's a small segment of the market that wants that halo maximum performance and will pay for it. So if you only have one chip, which is all we could afford to design at the time at the company, if you only can do one chip, you can't do the most expensive thing because it's just too small of a volume space. So we decided we would split it up into 4 and design a special on-package interconnect that communicates our Infinity Fabric protocol between the die, so that these look effectively like a single SoC, because this is just our on-die buses extended across package routes. And now we could get those 32 cores, but it costs 40% less than a monolithic version. We also got a lot of configurability. That chiplet overhead ended up being about 10%. Even with that, we get these large cost savings for the reasons I just covered last slide. So that was 2017. In 2019, we needed to do a follow-on that expanded on those capabilities to keep up the compute treadmill, and a deeper look at that single die that we designed with the Zen cores shows that the CPU compute area was only about 56% of the total. The rest of the die was Infinity Fabric Interconnect. It was DDR, as you can see here, die-to-die connections, and PCIe interfaces. Well, many of you are well aware that as we are scaling our devices into more aggressive future nodes, the analog and I/O circuitry does not scale very well at all. It doesn't make good use of that advanced technology. We're often bump pitch limited, or we are just analog circuit limited. So we needed 7 nanometer to get the performance, but we couldn't afford to waste that expensive silicon on stuff that didn't benefit from it. So we looked at ways to pop out the CPUs into their own little chiplets and wrap around them the minimum of overhead circuitry, connect them to the analog and I/O that was still required for the platform. And so what we ended up with was a 7 nanometer chiplet down here at the bottom that's 86% CPU rather than just 56%. We have the on-package links here in the middle, and then the chiplet test overhead and such that's required. And this made much better use of that 7 nanometer silicon. And better yet, we could relegate all of the analog mixed signal interfaces, DDR, et cetera, to the prior generation node, which is cheaper, significantly cheaper per millimeter squared. So we have these small, efficient 7 nanometer core chiplets connected to a different technology, central I/O die. This had a lot of advantages in that we had lower memory latencies with this centralized die, and we could populate varying numbers of these CCDs, we call them, CPU chiplet die, around the IOD to provide that configurability for the market. So this has ended up being a very successful architecture for us. Now we had to solve a number of problems to make that happen. One of them was, before it was ambitious to have a 4-die MCM, and there was a lot of concern about the test and manufacturing of doing that. Would we be able to route everything up because all those die have to talk to each other? Now we were talking about a 9-die MCM, which is pretty much unprecedented on organic substrates. And in order to connect these far CCDs to the IOD, because remember, all of these need to look and behave like a single monolithic piece of silicon, they need to be tightly connected, which meant we needed to route under these near CCDs to get to the far ones. We still needed to route the same PCIe SerDes links north and south, and all 8 DDR channels left and right. So we are making maximal use of the routing layers on this package, and we had to iterate on our silicon floor plan to ensure that we actually could do these routes and fit all of these signals together, because we were at the limit of routing layers in the package. A lot of silicon package co-design had to occur to enable this integration. And just one example of that was in how we would route underneath the CPU chiplets. As I showed here, we had to route to the far one underneath the near one. Well, in our prior generation silicon, we were already using that under CCD package routing layer for distribution of the memory rail for our caches. So we have these big L3 caches. Bit cells don't have the same voltage range as logic cells, so we generate a rail for them, and we use a linear regulator to do that. But now we needed our signal routes if we were to connect all our chiplets together, and so that's what's shown here. And so we had to do a significant redesign of the L3 cache and the linear regulation for that special supply rail. And we embedded that regulator striped along the L3 in the silicon and used on-die RDL instead of the package plane to redistribute that regulated supply. It was more resistive, so we had to cut the power consumption down in the L3 by 80%. We had a significant loop here of design changes that enabled the package routes that were required. That's what I mean by silicon package co-design. So it's a new level of innovation, and it's required that our package teams are tightly interconnected with our silicon design teams and are involved much earlier in the process. In the past, we would just throw our monolithic silicon design over to the package guy, say, here's the bump out, look it up, and everything was good. Well, now it's a completely different world where they communicate their package route constraints, and we have to adapt the silicon. Maybe we have to design new circuits, change our architecture. So fun engineering challenges, but it's a different set of skills. There we go. Okay, so now talking a bit about the modularity that I mentioned before. One thing that this chiplet approach has enabled for us is with the same design. Now, granted, this is just a CPU, not an accelerator at this point, but you can see the trend, right? With the same design, we're able to leverage these CCDs into different markets. So the desktop server market requires high performance CPUs as well, but it needs fewer of them. It needs less memory. It needs a different mix of IO. So we were able just to chop off essentially a quarter of that big server IO die in the middle, do a special one for desktop, and then populate 1 or 2 CCDs on a much smaller package and do this on a very short schedule with a lot fewer resources than if we had had to do another full special SoC for desktop, especially with multiple core counts. Now, there are challenges with this too. You know, the bump metallurgy had to be adapted, and the bump heights matched using copper pillars and other innovations. But once we solve those problems, we can now mix and match and trade silicon between markets to provide great compute performance in different mixes and different power levels. I can pause for questions on this if there are any.
So Sam, had a question here. In this integration here, does it make sense at all, given you know where AMD plays in the market, to actually have DRAM dies inside the package?
Yeah, so that's a good question. I know, you know, Apple does that in their M1. The putting DRAM in the package is it might make sense for some vertically integrated markets, but there's not a significant latency savings versus going off package. So that's like the first order performance benefit of, or the performance improvement you'd be looking for with that. But it turns out the flight time through DDR and the flight time on package just aren't that much different. So not much benefit there. It would enable a smaller footprint on the board, but if you do the cost calculations, the organic package silicon is a lot more expensive per millimeter squared than motherboard area. So if we have to grow our organic package to shoehorn DRAMs in there, the overall cost equation isn't in our favor. And then our customers, like our OEM customers, like HP, Lenovo, whatever, then they're stuck with one size of memory footprint in general, unless we're gonna, you know, square our number of product offerings. Whereas if it's off die, they can populate varying numbers of DIMMs, and that provides the flexibility they need. So the answer is not likely.
Got it. I mean, also, if you're buying, like, you know, known good DRAMs from a DRAM manufacturer, it's not like you're going to be able to up much in terms of a margin for co-integrating everything together, right?
That's another, yeah, the margin stacking problem, right? So we got to buy DRAMs from a vendor, they put their margins on it. And then if we're going to sell that as part of our product, we've got to margin that up, because the market will kill us if our margins drop too low, right? Because we're giving them DRAM at cost. Whereas now they can, you know, with today's model, they can buy their DRAMs direct from the vendor and only pay that margin once instead of twice.
Got it.
Now I should temper that by saying this is the client market and traditional server market. In our compute markets, we use high bandwidth memory, right? HBM to connect to our GPU accelerators. And HBM is too high bandwidth, too many signals to connect off package. It has to be on package. And so that in that space, indeed, we need to put HBM right next to the GPUs.
Got it.
Package.
So you read my mind as to where I was going to go with my next question is, I mean, this technology you're using, integrating 9 dies, so forth. This is like on a package substrate, multi-chip package or a multi-chip module, so to speak, right? I mean, for HBM, obviously, with the 55 micron bump pitch for the memory, you need an interposer-based technology, which AMD also uses. And I mean, does it not make sense from a cost perspective, or are there other technical reasons, perhaps, why it just is not feasible to even entertain silicon interposer-based substrate for this type of integration?
This type of integration. Great question, Alvin. So that I did a very extensive analysis of that. In fact, that was the first approach that I targeted for this 9-die MCM here on the left. It was interposer, right? And there's a lot of reasons, because yeah, it alleviates a lot of this package routing challenge that I just went over. It's lower power. You can fit the die closer together. There were a number of issues we bumped up against, though. One was it would have to be a gigantic silicon interposer, which would exceed the reticle size. And at the time, that was not manufacturable. But the other, and then there were reliability challenges with such a huge interposer, and thermal coefficient mismatches and flexing and stuff like that. And then finally, the problem was, if you can see these CCDs, this IOD here is pretty big. It's 26 millimeters across, and our reticle, so we get 2 of these in a reticle, but we can't grow it X and Y because we're at 26. If we wanted 64 cores, which we do, it would have been very difficult with an interposer to get the proximity, because interposer routes have to be pretty much in a 1 millimeter kind of max route length, because it's just this, it's not a transmission line, it's a resistive interconnect, right? So we would have either needed much bigger chiplets, which don't yield as well, and we don't have the configurability, or fewer cores, which wouldn't have been as competitive. So there were a bunch of reasons that the organic was just better.
Got it.
And I should mention the cost too,
yes.
right?
I was going to get to that.
Yeah.
I mean, would that be a non-starter, or it was actually in the realm of possibility?
It would be in the realm of possibility if it enabled reducing layer counts on the package itself. This package is pretty expensive, but it turned out the SerDes and the DDR routes required the full complement of package layers, regardless of our on-die routes, if we did it right. So given that we could figure out how to cram these chiplets in and route under them for the die-to-die connections, we didn't actually grow the package layer count. So this was hands down cheaper than the interposer.
Got it.
And that was a big reason.
Makes perfect sense. I do have a question that came up related to chiplet integration. Right now, I mean, does it require custom PD and CAD development to do this integration?
Does it require?
So I mean, basically, is it
say,
something that's off the shelf tools from CAD vendors?
Actually, it is. Yeah. No, it is it can be accomplished with off-the-shelf tools. Now you need the signal integrity experts, all the usual, for these high-speed links, and obviously the power consumption for these links is critical. So you need great analog engineers to design these. But the tool set, yeah, no, this isn't. That was the great thing, is this isn't really brand new capabilities, right? Like 3D stacking requires a lot of just pioneering development. This was more evolutionary and made it more executable with legacy approaches.
Got it. Another question. In the second generation architecture, why are the bottom 4 CCD placed in a square pattern instead of just in a straight line? like shown in the block diagram on an earlier page. Wouldn't it be easier for interfacing to the I/O chiplet to have a single row?
Yeah, that's well, for one, because we can't route these high-speed SerDes, see the power delivery to the CPU cores requires a full pattern of vias underneath that go down to the package core. Because the CPUs consume a bunch of power, and the way we floor plan this, the L3 is in the middle, and that enables us to route those signals like I went through, right, by integrating the BDDM plane. So the L3 is much lower power density. We can route under it. We can't route under the cores because of all the power delivery requirements. So if we were to line up 4 CCDs in a row, we would have to have cores over these SerDes routes in the middle. And it would have extended also over the DDRs. And that's just not viable because the power delivery to the cores would punch vias through those route layers.
Makes sense.
Sam, Alvin.
Yeah.
So I have 3 questions. Maybe we have time for one question and leave the rest to the later after the talk. So the first question from Harry is: it seems to me that the chiplet approach, the testing and the packaging cost will go up considerably, impacting profitability. Any thoughts on this?
Yeah, the testing, there were new test capabilities required to enable the binning of these CCDs so that we could mix and match. We didn't want slow ones paired with fast ones, right? But we already had a lot of that infrastructure in place, and I presented on our AVFS approaches and other things where we integrate on-die performance monitors that assess silicon speeds. Anyway, so there was development on the test side, but not a significant cost increment. On the package side, in fact, I just mentioned it in answering Alvin's question, we needed all these package layers just for the basic functionality of the server socket, and our competitors need those layers as well. And we managed to co-architect the package and the silicon so that we just, we did the routes using those same layers in a smarter way. So the overall cost increment is quite small. Okay, we better go. Do we have a hard stop at the hour, Alvin? Or
we don't need to, but yeah, folks are going to start dropping out in an hour for other meetings and so forth. But yeah,
okay.
I think
I'll move quickly, right? So that that silicon, that chiplet architecture hopefully gives you an overview of the innovations required in that initial step. Obviously, that's just a start on the chiplet architecture path. And we've made announcements here about our 3D product that we'll be delivering later this year. And we already touched a little bit on 2.5D and interposers. There is a smorgasbord of package options out there that that can be used to enable this sort of chiplet integration in different forms. And they all have their strengths and weaknesses. So we're looking at these from a performance, power, area, cost perspective. PPAC is kind of all-encompassing view. The organic package was by far the best PPAC because we were just reusing what we already needed to manufacture in that organic package. There are other approaches, competitors are out there doing embedded silicon bridges and microbump 3D stacking. Those require more special tooling and capabilities in the package manufacturing line than just generic organic approaches like we had. But they provide some additional density, right? Is that an overall win? Well, you have to, do the evaluation yourself on the merits. Similarly, these build-up approaches like info and wafer level fan-out, they have different pluses and minuses, and for some applications like connecting HBM to an SoC, they may be a better approach. And then we get to 3D stacking. What we unveiled there at Computex was a hybrid bond approach where TSMC is manufacturing an SRAM 3D stacked on top of that CCD that I just discussed using through silicon vias. And that provides much denser interconnect, but obviously has its own set of manufacturing challenges. So, you know, I won't spend time on this, but this is just an example of figures of merit that we use to evaluate these package technologies, the aerial bandwidth density, the linear bandwidth density, which sets the amount of beachfront required to connect a given number of signals. And then there is the speed capability of the channel, et cetera. And so all of these things have to be put together in an equation to determine what makes the most sense. And I've tried to illustrate it here, right? As you know, the EPIC chiplets, it's really a 2D approach. The interposer approach, and thanks to Alvin's question, I already talked quite a bit about some of the puts and takes. Silicon interposers, you get more density, but they cost more, and they also limit the reach of those signal routes relative to transmission lines. But then with 3D, we get much lower power interfaces, much higher aerial bandwidth density, but the cost adders are obviously much higher. Also, we end up with much more severe restrictions on the silicon floor plan, right? These sizes have to be matched and the interfaces are fixed, whereas you get a lot more flexibility when you can put them in a 2D design. So the engineering complexity here is higher. And you put all that into this equation, right? So we really look at this at the, you know, value perspective. You know, is the customer going to pay more for this modular product? We get more capability in there. You know, we have kind of compute acceleration they're going to pay for. Then there is the yield, and you know, if we use heterogeneous technologies, we can get the cost down. So those are the positives. And then the question we have to answer, are the positives bigger than the overheads? You know, we have to add chiplet overhead. Package might get more expensive, certainly with interposers it does. You have to subtract the power cost of the interconnect from your overall compute budget. And then we only have so many engineers to design these things. Is it just too complicated? If it's too complicated, then we miss our time to market window. We don't yield it. That's a loser, right? And so this is one of the big factors, is addressing the complexity. So it's a multidisciplinary optimization equation, and I spend a lot of my time, and across the industry, this is going to be a bigger focus to me. Maybe I'll pause there because we're almost out of time, and this was really the meat of presentation. So if there are questions.
Yeah, so Sam, more questions. One question relates to how the dies are interconnected together. I believe it's a proprietary link that has been built, right? An infinity link, is that correct? To connect between the dies?
It is. So it's our on-die fabric, we call it. And it's the same fabric that we use in monolithic silicon.
Mm-hmm.
But we have different, we can adapt that protocol based upon the interconnect capabilities of the link. So like in the 2D approach, we actually packetize that link. So we add some latency to neck these on silicon buses down to a narrower format and packetize, you know, serialize essentially the communication, and then we expand it on the other end.
Got it.
If we get,
sorry, go ahead.
Well, and I say if we get more connection density, we don't necessarily need to do that packetization. And like in the 3D space, we have so many signals that we can just use the raw monolithic silicon interface protocol to direct connect.
Got it. I mean, there's a question that asks, you know, if it made sense to use like a standard, like say a PCI Express connectivity between the dies, if you know, that would increase overall system power consumption. But I would argue with PCI Express, you probably lose cache coherency and a bunch of other things for a link that you really don't need. I mean, it's a short link, so you really don't need all the bells and whistles of a PCIe link, right?
Yeah, I mean, that's viable. Like if we wanted to replace one of these chiplets with an accelerator or an FPGA, um, PCIe would work great for that. But whenever we want this thing to behave as if it were a monolithic piece of server silicon, we need that full coherency. We need the low latency. PCIe comes with a lot of latency. It comes with 8-ish picojoules per bit. We're down at 2 picojoules per bit with our proprietary. So yeah, it definitely not general, it's not applicable for this application.
Got it. And another question, obviously there's no shortage of interest in this topic, right? Approximately what die size does the chiplet approach start to make sense?
Yeah, that's a great question. So that's completely a function of the yields and the cost of the target technology, and it depends on whether you're going heterogeneous, right? So if this middle die were 7 nanometer silicon, it'd be super expensive, right? But it's in a very mature, high yielding 14 nanometer, lower wafer costs, So if we made this thing monolithic, it would have to be entirely 7 nanometer, and all of this IOD content would be in that expensive 7 nanometer, and much of that IOD wouldn't shrink because it's analog.
That's right.
So the cost trade-off point is different when you have this sort of partitioning than if you just take, say, a GPU that's almost entirely logic and do the calculation of partitioning there. Yeah. If you do that latter one, we found that with the overheads and such, for a mature technology, around a 200 millimeter squared starting point is kind of like an inflection, where if your starting SoC is bigger than 200, chipletizing makes sense. If it's smaller than 200, maybe not with today's approaches. But as we get to more expensive technologies and as yields diminish, right, then that break-even point goes lower.
Got it. And I'm assuming, I mean, it seems like the very logical thing. The partitioning was architected such that for future AMD products, that same 14 nanometer IO hub die will remain the same, but then the 7 nanometer dies will be replaced by 5, 3, 2 nanometer dies, etc. Right?
Yeah, that's definitely one of the benefits. You can upgrade the components independently. Yep. Or maybe you have a different IOD that has a different mix of memory and SerDes or a different protocol on it, right? But you reuse the CPU chiplets.
Got it. And there's another question, a slightly different topic, this one on security. What about security considerations between the chiplets? What about supply chain attacks of someone replacing a chiplet by a compromised one?
Reworking these, popping off one of these and having a footprint compatible version inserted that's going to function, that's beyond the kind of attack that we've considered.
Yeah, well, it's probably going to destroy the part in the process of doing that anyways, right?
Yeah, so that one's tough. But yeah, I mean, security is front and center, and being able to, like, could someone intercept these die-to-die communication links and decode the protocol? So that is a concern. We believe we've addressed that with a lot of our security features, but definitely a consideration.
Or you could build in crappy ESD, for instance, of the parts, such that when you try to take out a part, you'd end up destroying the other parts.
Guaranteed destruction. Yeah, yeah.
Yep. Yeah, those are all the questions I have. Jeff, did you see any questions come in?
Yeah, yeah. I guess I have a couple here. Some of them already answered by Sam. Let me see. Yeah, security is also answered.
Yeah.
Okay, so there's a question saying that what's the impact to the software in transitioning from monolithic SoC to chiplet architecture? Milan.
Yeah, that's good. And our goal here with this, actually with all of our chiplet architectures disclosed thus far, is to have it be software transparent. Now, one of the problems we had, and I don't know if I want to flip all the way back, but maybe I will, with this first generation, is the latencies were non-trivial between these die, and the memory interfaces were local. So we ended up with 4 on-die NUMA domains, non-uniform memory access latency domains. So this was actually software visible, in that if the application running on these cores over here needed to access memory from the die on the opposite corner, it paid a significantly longer latency than if it were accessing local DDR here. And so for optimal performing software, they needed to be NUMA aware and co-locate the applications with the memory, et cetera. So that was a weakness, and we addressed that pretty much completely with this centralized IOD approach, where every chiplet just goes to the IOD, has very similar latency to any of the 8 DDR ports. So that means that this one on the right was pretty much software transparent, chiplet versus monolithic. And that really is our goal in architecting these, because software is probably the hardest thing in our computer design, our processor designs, right? And similarly with this 3D, it's just a bigger cache that behaves identical to the hardware managed single layer cache, and the software just transparently gets the benefits.
So I have one more here. Does the Infinity Bus support hardware cache coherent policy among CCD caches? And if so, what's the cost? From Gary.
Yeah, no, it does support hardware cache coherency. What's the cost? Well,
I'm sorry. Was the latency a problem? I'm sorry. Yeah.
Yeah. So I mentioned the memory latency. We largely solved that by centralizing the memory interfaces on this one IOD. But obviously, if the chiplet on the left needs, determines, so what happens is the chiplet on the left will try to access memory. Maybe it gets a miss, and then it checks the probe filter in the IOD, and it finds out the line is over in this other chiplet. Then this other chiplet needs to send the line across through the IOD. And indeed, that is a latency that can impact performance. Now, we have worked very hard to reduce this cross-die latency to be just 13 to 15 cycles. So it's not that much when they're running at high frequency, but it's noticeable, and obviously we'll be improving on that in future architectures.
Okay.
But good questions.
Cool. Well, hey Sam, we've taken enough of your precious time. That's all we have on this side. Thanks so much for taking time to go over. This is just incredible innovation that AMD has accomplished here, and I really appreciate you sharing and being so transparent with this.
Yep, always fun to talk to fellow engineers. Thanks, Alvin.
It's my pleasure. Anyways, thanks everyone. Stay well, and we're riding hopefully till the tail end of this pandemic, but this pandemic has certainly given us the opportunity to have Sam here, and Sam, definitely we need to bring you back to your hometown.
Going to San Diego is not a bad option. So yeah.
It's rough, but someone has to live here. Yeah. Yeah. Okay, great. Well, thanks again, Sam. And I guess we'll be in touch with you shortly. Certainly we look forward to hosting you here in San Diego sometime in the not so distant future.
Sounds great.
Yeah.
All right.
Okay. Take care, everyone. Have a great weekend.
Thank you, everybody, for joining the talk.